Okay, time to take another attendance. So when people come in, just pass them to the new to the people come just join the classroom. For those who are on Zoom, you don't need to do any attendance because everything is recorded, so I can see who is there, who is not. So we're gonna continue to talk about the optimization. The optimization. This is again. I realize this is this is probably just okay. This is probably just a refreshment for the what you have learned in the undergraduate class. But I view this is very important for you to. This is sort of like set out for the next week. In the next week, particularly, not just next week actually, is for the next week and also the algorithm in the following, because when I talk about the introduce the ADMM in the next class, and also for the SVM in the like the motivation or the algorithm behind the SVM. We do need this is an optimization condition to be like the knowledge to be there to fully understand the material. Particular things like duality, the optimization problem. Okay, so those are essential. So this is again, it's if you already know most of stuff, that's perfect fine. Just consider this as just as a refreshment of your memory. But if this is like it's hard to, okay, then you need to be spending the time to understand, go through all those materials more carefully. So for the unconstrained optimization, okay, unconstrained optimization is this is just as name said, we have object function f, which is defined on some interval a and b. Now, but without there's no additional constraints. Okay, of course, this can be viewed a constraint. Like if it's on interval a and b, that means you have to be somehow to be inside this region, right? But this is a general approach to say this is the a and b could be negative infinity and positive infinity, right? So this is but then let's say we has to be narrowed down to some very large number b upper bound and also very large lower bound a. So then if we have this, suppose f is unimode in between this a and b, how we can find this is how we can find the minimum amount for the of the f with this interval. Okay. Now, if we have, suppose we have 2 points, x1, x2, within this a and b, just without loss of generality, we assume x1 is less than x2. So we can evaluate comparing this is f x1 and f x2. Okay. Now we can discard either x2 to the b or a to the x1 with the minimum known to be lie between in the remaining subinterval. Then we can repeat the process, and we can we just need to compute only one new function evaluation to be able to continue to the next iteration. So to reduce the length by fixed fraction at each iteration, okay, so each pair of point must have the same relationship with respect to the new interval that the previous pair has respect to the previous interval. So what does this mean? This is actually corresponding to this is so-called the golden the golden search algorithm. Let's say, okay, you have a function. Okay, you have a function defined between interval between a and b. Okay, you have x1 and x2. You choose two points. Now you suppose you have an interval. This is suppose function f is unimode, right? Now let's say you draw a function somewhere like this. Okay? This is a function. Of course, you have A and B, right? Now in between you have two values. This is fx1 and this is fx2. Suppose your fx2 is bigger than your fx1, okay? Then you know, okay, your minimum cannot be located into x2 and b. This region can be eliminated, right? Because the function is unimode, right? Unimode, that means since fx1 is less than fx2, that means on this side, okay, on this side, there must be some value is going. The function has to go down on this to the left of x2, right? So therefore, on the right side of x2, then the minimum cannot occur there. Okay, this is just based on the fact one fx is unimode, and then the fx is unimode, and therefore fx1 is less than fx2. So based on these two conditions, we know if this is minimum, if the minimum is if it occur on the right side, then this function is not unimode, right? If on the right hand side, then that means say this is minimum, then the function must have to be go down and then go up. So that's validating the assumption, the unimode assumption. So if fx1 is less than fx2, that means the x2 the minimum cannot occur between the fx2 and the fx3. So therefore, this region can be eliminated. Then we can constrain our optimization within this new interval a and x2. So if we have this ax2, we already have a value fx1. What do we need to do in the next iteration? We can just add in a new point, all right? A new point into the search. So this new point could be I didn't draw it very well. New point could be like here, okay? Then the new point, this is say this is x2 prime, okay? X2 prime. So then we can compare between the fx1 and the fx2 prime. This now the new problem. This is going to be x2 going to be the new upper bound, right? A is still the lower bound of the region, but it's the same. You're choosing. We can compare fx1, fx2 prime. See which one is larger. See now this case fx1 is larger than fx2 prime. So therefore, then use the same argument. The minimum cannot occur in this region, so therefore we can eliminate it. This is a lower bound a to x2. Then in this case, then this second iteration is done. So we go to the third iteration. We can set the x1 to be the lower bound and the a prime, and the upper bound is still the b prime, which is x2. Now you have one point, adding another point in between, and so on. So then you can iteratively, reduce your shrink interval, right? Until this is shrinkage to be a very narrow a region. Okay, this is going to go down very fast because this is you basically multiply by a certain fraction. So very quickly, the region is going to be, you can narrow down to a very small region, and that region is your minimum point. Okay, so with certain accuracy. So this is essentially this is what the algorithm this is what the algorithm talks about. Like the in word description is like this, but what I draw on the whiteboard is sort of like a geographic interpretation of that. This algorithm going to lead into the algorithm called the golden section search, right? So golden section search is to accomplish this, we choose the so-called relative position of 2 points, tau and 1 minus tau. What does this mean? That means if we want to B, right? This is B. Now this is your tau. This is sort of like your 1 minus tau. Okay. This is referring to length is tau, right? This is that's here. This is the 1 minus tau. Let's see if you choose yeah, we can Let me check my notation, see which way is easier to, actually, which way is easier to write. Either way, because it's just the goal, okay? The goal here is just to, okay. The goal here is to eliminate like a certain fraction from the data. So so x1, yeah. Let's just use in this notation because it doesn't really matter if I using 1 minus tau in this side. This is tau. Is just reverse. So say this is A and this is B, right? In between this A and B, we want to set up two points, okay? 2 points. The tau and the 1 minus tau. Of course, this is that's without loss of generality, okay? That's just using the upper bound and lower bound to be 0 and 1, okay? Because I can always shrink my A and B to be in the rescale to be 0, right? So it's just a scaling problem. That's fine. So I want to choose these 2 points. The reason is either way, okay? If I want to eliminate, so this will be my x1, this will be my x2. Sorry, let me important call. I need to take it. Just give me 1 minute. Hello? I'm teaching. So sorry for interrupting. The goal for this is we want to eliminate, if we eliminate the upper bound, this fraction is 1 minus tau, right? This fraction is 1 minus tau. If you want to eliminate the lower bound, this fraction is also 1 minus tau. So even by choosing this is a 2 meter for 1 point is this is 1 minus tau either, okay? Either way, if we eliminate the bottom section or the up section, these two are in both cases you're going to eliminate 1 minus tau percentage of the segments, right? So in these cases, then you can always have a fixed fraction. Now let's say, for example, okay, we having, so this is your x1, this is x1, this is your x2 is this. Let's say if we have in our upper bound, the upper section being eliminated, okay? So in this case, what you're gonna have is, so you're gonna have A is still be 0. This is B, now it's become like tau, right? This is the tau is gonna be your new upper bound. So you already have a point, okay? You already have a point, which is like 1 minus tau. Here, this is you already have a point, be your 1 minus tau. And this 1 minus tau, you can say I can set up to be x1, okay? This is given by x2 in the new setting. Now I just need to insert. I want to insert another point, x1 in here, such that this fraction, okay, this fraction and this fraction is also 1 minus tau of the second left. Okay, is also 1 minus tau second left. So therefore, what you have here is the distance between these two. Okay, let's say the distance between these two is going to be this is tau minus 1 minus tau. So this is going to be minus 1 minus tau. This is the 2 tau minus 1. Okay, this is divided by the whole length tau. This has to be equal to 1 minus tau. Okay, so if you have this, then you can do x1. Basically, x1 can be saying the distance x1 going to be equal to 1 minus tau times tau. Okay, then because this is you want this to be 1 again is 1 minus tau to here, right? So if you can have this, then you can solve this. This is if you solve this equation, okay? Solve this equation, you can say tau roughly equal to 0.168. Okay. Now this, of course, if you guys know this. This is called a golden section, right? So this is a golden number. So if we're using this is a particular fraction, okay, particular fraction, which is 0.618, then you can at every single iteration, okay, essentially this is what we see here. So we can choose if to accomplish this, we choose a relative position of 2 points, tau and 1 minus tau, where this is we can have this is a tau square equal to 1 minus tau. So this is the tau roughly equal to 0.618. If you do that, then every time when you're setting up a new point, you can every time you can just add a new point, and at each step you can eliminating roughly 1 minus tau, which is the 0.382% of the segment away. Okay, you can sort of like peel it off. So then this is called the golden section search, which is pretty fast. Okay. Now you can also say this is on the right side, right? You're limiting the so you're limiting the right side. You can have this, you can have that, how you put this. What about the elimination is on the left hand side? So if you eliminate on the left hand side, it's also the same, because in this case your B is going to be equal to 1. Your A is equal to 1 minus tau, right? So you already have a fraction here. This is your tau. The distance between these two is 2 tau minus 1 as well, right? The tau minus 1 minus tau is 2 tau minus 1. So you want this fraction, okay? So you want this fraction to be another point. So this is you want to be x2. This is going to be your x2 becoming x1, right? So you want to be 2 tau minus 1 over tau equal to 1 minus tau as well. So that means this fraction is also a fraction of 1 minus tau. So you can see they end up with the same equation, okay? End up with the same equation. So which means if you're using the this is a 0.618, this percentage to be the 0.618, this percentage, you can always, okay, you can always at each step you can remove 0.382% of the segments of you remove this interval, right? So that means you can shrink your interval is pretty fast. So whichever subinterval is retained, its length will be tau relative to the previous interval, and the interior points retained will be at a position tau or 1 minus tau relative to the new interval, right? So then you can continue iteration. We only need to compute one new function value at a complementary points. So the choice of this sum points is called golden section search. Golden section search is safe, but the convergence really is nonlinear within the constant, right? Of course, the C is roughly like a 0.618. Now, this is a so-called golden search can be. You can see here is basically is one-dimensional unconstrained optimization, right? You only have one parameter, and then you can search it through the sort of the sum interval, and you can sort of get in the you can get it done this done pretty fast. Now this relative days, right? Relative days. If you know a segment like A and B, if you know if it's one-dimensional, you can also do another kind of search. It's called grid search, right? You can if you just know your parameter is just one. If it's just one parameter, you can do grid search. Grid search basically is you can take an equal interval. Say you partition your interval into 10 segments, and then to find out the subinterval, which has the smallest with two bounds has like the smallest value. Then you can narrow it down to be like a small interval, and then you can do a search, grid search again with and go down. That grid search will be slower than golden search a little bit, but if it's one-dimensional, is actually not bad. So this golden search can be used for this actually can be used for the when you remember when we talk about gradient search, there's one parameter which is step size, right? So for now we haven't really talked about step size, how you can determine it. This golden search actually is a good way to find the step size, because when you are choosing the step size, which is actually it's a little bit further away. Like here, if we want to do the golden search, if we want to find the step size alpha k, alpha step size, you can actually view it as a parameter, right? It's a parameter you need to determine. So in this case, you can this is the problem to find it. You can determine this is a problem to find the one one parameter optimization problem. Okay, and this golden search can be used in it. Here is just the this is sort of like a pseudocode for how do you apply to this is a golden search. This is just to so basically you set a fraction, you set in your x1, x2, and then depending on the value, you can sort of like iteratively go through this. And the loop is going to stop until the interval length. Okay, interval length is less than some tolerance. Okay, this tolerance could be very small, like 10 to the negative 6, 10 to the negative 4. There could be some small value. Okay. So this is a golden search. I think is a pretty straightforward. You can but I think it's a pretty elegant way. Okay, it's a pretty elegant way to implement. This is a sort of like a one parameter optimization. Now the more general this is people is actually using Newton's method. This is Newton's method we already introduced before. So here is just like in a more like well, not formal. It's just I just put in the slides. Okay, so if you in case you didn't get what I said when we discussed a logistic regression, here is a slides to you can refer to. So another local quadratic approximation for the fx plus h, we can basically is say you have in some neighborhood you have a function, f, right, fx. So this is a function fx. Now in some neighborhood of x, okay, in some neighborhood of x, this is your fx value. In some neighborhood of x, you want to find in this neighborhood, okay, inside this neighborhood. Well, how can if I move this x a little bit, okay, if I move x a little bit to be fx plus h, okay, to incremental, either incremental or the decrease. This is my current point a little bit. So change it to the change the point to be x plus h, right? This h could be positive or negative, right? So it can go up and down. Now, then the question is, if you want to do that, where should we move? Right? So then we can just using the so-called the quadratic the truncated helix series. So let's view this fx plus h. H is our parameter, okay? Which is our parameter. Then we can expand it at x using with h, right? So then the fx plus h basically is approximately fx plus f prime x, which is the first derivative, plus the second derivative divided by 2 times h squared. Now, now the point is I want to find h, right, which can minimize this function. So if I can find an h that minimize this function, then this is can say I can move this is my update my x to x plus h, making the value small, right? So that's the idea. So by differentiation, the minimum this correct function h is achieved at the negative f prime x divided by f prime x, right? So this negative first order derivative divided by second order derivative. So this is then the suggested iteration would be if I'm currently sitting at xk, so I will updating my next data points by minus the f prime xk divided by f prime prime xk. So this is called Newton's method solving nonlinear equation. This Newton method for finding minimum normally has quadratic convergence rate, okay, but must be started close enough to the solution to be able to converge. So if you're having this is xk plus h equal to xk minus if we update this, okay, this is still just the gradient method, okay. This is still consistent with gradient methods. Why is consistent gradient method? Because if you have a minimum to be exist, okay, then your second this thing has to be positive, right? The second order derivative has to be positive. This is a condition for the minimum to occur. So if this is positive, this is basically saying you are moving into the opposite direction of the gradient, right? You are moving to the opposite gradient. So therefore, your function value can always go down. So that's this is a Newton's method. Now, instead, if you want to do the steepest descent method, which is we using the observation is at any point x where the gradient vector is non-zero, negative gradient, which is negative. This is a negative gradient of x. The points downward toward to a lower value f. So in fact, this negative gradient is locally direction of the steepest descent, which suggests equivalent to say f decreases more rapidly along the direction of negative gradient than along any other direction. So the steepest descending method basically saying we're starting from the initial gas x0, then repeatedly the solution is going to be xk plus 1 equal to xk minus alpha k times the gradient of the this is the function f at evaluated as k. Now this is this is essentially is equivalent to the Newton's methods and the gradient method when we discuss the logistic regression, right? So this is if you plug it into the logistic regression, this is the same. The only thing is for the logistic regression, we are doing this is what I see now is one primary cases, but for the logistic regression or for the other, we typically do multi-dimension. So therefore, then this is a gradient instead of gradient is a vector, is called score function, right? Instead of the second order derivative, then we have a Hessian matrix. So that's is just the extension to multivariate cases. This alpha k, okay, alpha k can be done by a line search, which essentially can be done by the grid search of the parameter, determines how far to go in any direction. Now notice here, this alpha k, you don't have to be laser accurate, okay? Which means you don't have to be this alpha k. You don't have to be exactly at every step. You have to be like making the largest step to be able to moving toward to the minimum, okay? So alpha k could be just be a ballpark. It can just be like in the direction of negative gradient. You can just go down in the negative gradient. It just depending on if it's go too fast, it's gonna be like if it's too large, then it's gonna help you at the beginning, and then but the main point is and when it's close to the end of the search, alpha k cannot be too large. Otherwise, it's gonna oscillate between your optimum point. So then this alpha k typically people just do one like a very coarse search by dividing your like to be your interval to be like 5 times and then find out like find a neighborhood of the x, right? So then you do a sort of like a line search to see which alpha can give you like reasonable update to the sk. Then you can just keep your at this step we don't have to go through this is find the exact minimum. There's no need. Okay, so that's this is for the step size. So given the descent direction, such as negative gradient, determine a probability of k is one dimension minimization problem, right? Because then you know your xk, you know the gradient, right? You know the function f. You plug it in, right? This is in this function right here. That only alpha k is unknown, right? So therefore, you can actually solve this by the golden section search or by the grid search or by line search, right? So it doesn't. This should be pretty easy to solve. And then the steepest descent method is very reliable. It can always make progress provided gradient is non-zero. Okay, so but this method is myopic in its view of the function behavior, and the resulting iterations can zigzag back and forth, making very slow progress towards solution. So in general, convergence rate of the steepest descendant is nonlinear, okay, with constant factor that can be arbitrarily close to 1. So this is sort of like the thing we already seen for the unconstrained optimization. So again, it's just serving as a reflection memory, and also it's just almost the same as what we have for the logistic regression. Okay. Now let's talk a little bit about the constraint optimization, the equality constraints. So this is what we just talked about previously is unconstrained optimization, right? So when you say moving in the direction of the gradient, if you're sitting from xk, you basically can move in anywhere. So there's no constraint. Now, if we're adding constraint to the optimization, constraint optimization, you can break it into like two small error. One is your constraint is equal constraint with equality, right? And another constraint is inequality, which is so that's these are two different the scenario. So let's briefly go through. This is the both scenario, and eventually what we want to come up is a KKT condition, okay, which is that KKT condition, which is will be useful for us for you to understanding like the following the material. Because I'm pretty sure, okay, I'm pretty sure you guys, if I go through this material, you're probably gonna ring a bell in your mind. But if I don't go through, if I jump directly to say KKT condition, some of you probably have to think like what is KKT condition. You have to sort of like getting basically it's may become a little bit rusty on that part. So this is just very quickly, okay, this is very quickly to get into our the leading to the what we want to get, which is a KKT condition. Then from there you will be able to understand the next week's lecture better. So for the this is a constraint optimization. Let's just illustrate using simple example, right? So this is a tutorial example. So what we try to do is the problem is we want to minimize some function fx, okay? And this fx, see the x is two-dimensional, okay? Is you have two x1, x2 is two-dimensional, and then subject to some constraint. This constraint is hx equal to 0. H is some function, right? It is another function. So this hx equal to 0. Say for example, your fx could be x1 plus x2. This is just to be referred to a hyperplane, right? This is to be say this is a this is just if you in a two-dimensional space, this is basically a plane. Now let's assume your hx, your constraint is x1 squared plus x2 squared minus 2. So this is set equal to 0. That means x1 squared plus x2 squared equal to 2. That is a circle, right? That is a circle. Now, without constraint, okay, if we don't have any constraint, without any constraint, then fx in this case is just to denote could be the intercept of this function, right? So x1 plus x2, x1 plus x2 equal to 2. That's basically representing a line going through this going through these 2 points, and with the intercept is equal to 2, right? So and then if you don't have constraint, this function has no minimum. Right? This function has no minimum because this is function. What's the minimum for this? Is if without constraint, it's going to be negative infinity, right? So you could be x1 go to negative infinity, or x2 go to infinity, or both go to negative infinity. That's we don't really have a minimum point. And then for this problem, of course, is not interesting. People not really interested in that one. Now, if we add in a constraint, okay, hx equal to 0. Now hx equal to 0, that's as I said, that's essentially is a circle, right, with the radius equal to square root of 2. So then all of a sudden your x1 plus x2 can no longer move anywhere anymore. Okay, it has to be, it's going to restrain in this circle. This circle is a pretty small space. If you just look at this graph, okay, you can see the minimum point is going to be achieved at this point right here, where the line x1 plus x2 minus 2 is going to tangent, right, to the circle. This will be the point you're going to achieve. The minimum point basically is you're going to move the line in parallel through this circle until its intercept to be the smallest, right? Its intercept to be the smallest. Then that point is your minimum point, which is the values right here, right? Values right here. Now, the minimum point is well, minimum point actually is no, the point actually is not x1 plus negative 2. It should be negative 2 times square root 2, right? Because this is this guy right here. It should be square root 2 square root 2. Okay, so this is actually the illustration actually is a little bit wrong. Now but this is the number is not important. Okay, the thing is we try to, if we look at this is we just move the line in parallel until its intercept is smallest, and also still can touch this region, right, which is in this case will be tangent line. Now we can solve this for this particular problem, right? Now if which one? It's -1. It's going to be negative square root 2 and negative square root 2, right?
I think -1.
-1? Wait,
yeah, like hx is 0 at
-1, -1. Oh, yeah. So this is actually correct. Yes, you're right. Square root of square root actually that's equal to 4. Right. So yeah. So that's right. So this is actually correct. I was a little bit confused. Okay, thanks for putting that. Okay, so now the question is there a general the mechanism to talk about this, right? Now think about it, right? So if we given a point, some point xf f on the constraint surface, right? So because this surface, this is our so-called feasible region, right? Is if you want to find some minimum point, the minimum point has to lie on the circle, right? It has to be on the circle. Now, so this is a feasible. Let's say we have some point f x f. Okay, this is f, which stands for feasible. So then, how can we move this point a little bit to be able to? So our goal is we want to move this is the xf a little bit, with two things to be to satisfy. One, we move this xf a little bit. So this is a feasible point. This is still going to be located in this circle. Okay, so that means you still want to be the so you want to so given we have xf. Now if we want to improve, okay, if we want to improve this xf plus some delta x, right? So if we want to what I wrote down the room, what I wrote down the blackboard is given we have a point xf with a feasible point, and then we want to improve this xf a little bit. Now this improvement need to be at two conditions. One is this is the h of, you still need to be 0, right? Need to be still on the located in the feasible region, right? The second, I want my target function, okay, or objective function to become a little bit smaller, okay? So that's two. So if I want to improve, if given I have a point, feasible point SF, and I want to improve on it, then I want this is to be, these two things happen, right? I move a little bit by adding a delta to the fx. Then I want it to still to be feasible, and also the function to be go down a little bit, right? So that's this is what I want. Now, in order to do that, okay, yeah, so I want to find such delta x such that this is still whole, and also this is the target function is going to small. Now the question is how do we do that? Okay, how do we do that? We can do this is like by two things, right? So one is we know in this is in the delta x we can move any direction, right? So delta here we can move to any direction. Now we know for the fx which is so our fx is equal to x1 plus x2, right? So we know the gradient. What is the gradient? The gradient will be, the gradient is going to be 1, 1, right? This is our gradient. So the gradient is, because gradient is just search that is the dfx dx1, which is 1, dfx dx2, which is also 1, right? So your gradient of the target function is 1, 1. So in another word, what do you have here? Your gradient basically is pointing to this direction, okay? So the gradient of the, this is a gradient of fx, right? So this is a gradient of fx. Now, then the gradient, so the gradient for the hx, okay, the gradient for the hx. Now, gradient of hx, you can see is a circle, right? And each circle is radius actually is going to go down. So, and we know the gradient of hx is what? Gradient of hx, this is essentially that's equal to the 2x1 and the 2x2, right? Because you're taking the derivative of this is 2. Then the gradient actually is pointing to what? Is pointing to the is orthogonal, okay, or the perpendicular to the surface of the circle. Okay, that's the gradient. That's the gradient of x2, or gradient, not x2, gradient of the hx, right? So let's set it up to the on the side. So the gradient of fx is equal to 1, 1, right? That's this is the gradient. The gradient of hx is equal to 2x1, 2x2, okay? 2x1, 2x2, that means basically if your x1 is here, x1, x2 here, then the gradient just point to that direction, right? So which is essentially saying this is our gradient is perpendicular to the surface of the of this hx, okay? So that's a gradient. Now, in order for us to moving our target function, okay, in order to be for this condition to be satisfied, our delta x has to be in the negative gradient of the it has to be aligned with the negative gradient in the target function. Okay, so in order to move that, then that basically means our function, the delta, which has has to contain some component for this is a for this negative gradient. Okay, and we know negative gradient is 1, 1. So the gradient is 1, 1. So negative gradient is -1, -1, which is point to the to this direction, right? Now, however, when you try to move the point, you don't have to be moved in the exact direction of negative gradient, right? Because when you move it, if you move you move it in this direction or move to this direction, they both is going to decrease your target function, right? Because as long as it has a projection, okay, as long as a projection has to be projected to the negative gradient, as long as this projection is non-zero, then it can go in the direction of negative gradient, right? So, but if you go into this way, okay, if you go into this way, then this is not going to increase. This is not going to decrease the function because now the projection to here would be have positive gradient, right? So therefore, your gradient in here, then your function or the dirt x, essentially, you want your dirt x multiplied by the gradient has to be positive. Okay, as long as it's positive, then this is fine. Okay, this is fine. So to summarize this, the condition to decrease the cost function, okay, condition to decrease the cost function is saying the direction of your move the dirt x multiplied dot product. This is a dot product, right? Dot product of the of this negative gradient. As long as it's positive, you can decrease your target function. Okay, so this is the first condition you want. You want this dirt x dot product of this is a gradient. There has to be bigger than 0. Again, like I said, is we don't have to be saying the dirt x to be in the exactly same direction of the negative gradient. As long as it's in that direction, okay. As long as it's in that direction, then this is you can making your cost function or target function to be smaller, okay. So that's so this is the first condition we want to satisfy. So this condition can make sure this to happen, right? To make sure this to happen. Now, but we still have another one thing to do. We need to making our point after move dirt x still feasible, okay? Still feasible. So then the gradient, like we said, the gradient for the constraint function, essentially those are the direction perpendicular to the surface of this circle, right? The surface of the circle. And this is true, okay? This is actually true for anything. If you have this surface, any the gradient is going to be perpendicular to the surface. This is true for every for all the functions. So these are the norms to be constrained given in this direction. Now, of course, then if you want you point inwards, the inwards, this is just to be saying we can be the function is going to be negative gradient. Now, no matter you going outside or going inside, okay, as long as it's in the direction of the in the direction or which is of the negative gradient of the cost function, it can decrease in value. But if you want to make your function to be doesn't change, okay, you have to move, you want to move in the direction of this gradient, right? But just by a little bit, right? By a little bit. So the direction of the norm is arbitrary, as a constraint can be imposed either by hx equal to 0 or negative h is equal to 0. That basically means either way you can move in the direction of this is the gradient of the constraint function or negative gradient called the constraint function. It doesn't really matter, right? Because this is both can be the both can making this the constraint still be satisfied. So if you move, okay, if you move in the direction of the gradient, this gonna be making, you're gonna making your gradient, if you move in the direction of the gradient, either in the direction or the opposite of gradient, your constraint function value is gonna change, right? So if you don't want it to change, so what are you gonna do? You want to move in the direction perpendicular to the gradient, right? So the only way you can move a function, which is the only way to move the function that doesn't change your function is when the direction has no projection to the gradient, then you can keep your function the same, right? So therefore, to make sure your constraint, okay, you're moving some delta x, okay, you move some delta x, but this delta x has to be still keep this the same. So then the delta x, we have to see the delta x multiplied by the gradient of this is a multiplied gradient of this is a constraint function. They have to be 0. Okay, so therefore, let's say let's go back a little bit. So in order to be this satisfied, the delta x, okay, dot product of negative gradient of fx, this has to be bigger than 0. Okay, so as long as this is your direction of movement and the negative gradient cost function, as long as they're same direction, you can make in a second to be satisfied. Now, in order to make this to be satisfied, okay, so you want your delta x and the gradient of the hx, you want this to be 0. All right, so you want this to be 0. That's for those who are on the Zoom. That's basically saying you want to make sure your gradient delta x, delta x times this is a gradient of hx, it have to be equal to 0. So if this can happen, that means your movement is perpendicular to the gradient. So therefore, it doesn't change your constraint value, right? It's still basically your new point is still going to be feasible, okay? Still going to be feasible. Now, if you look at this, right? If you look at this, then we can see the movement is pretty straightforward. So say if you are in somewhere in here, okay? If you're somewhere in here, so this is your new point. This is your new point, okay? This is a new point. So then you're gonna move. You're gonna move your line. It's gonna be. This is change the color a little bit. Right. So you're gonna move in this direction because this direction. First of all, you're gonna keep your point still in the feasible region, but it also is you can say it's can making your target function, cost function could be go down, right? Because it's still in the direction of negative gradient of the cost function. If in here, you're gonna go this direction, right? If in here, you go there. If you're here, you're gonna go down here until it reaches to a point where you having the gradient, it doesn't change anymore. So this point will be your optimum point. Okay, this point will be your optimum point. So now you can see this argument. Okay, now this argument is we're not really taking into the characteristic of this fx and hx particularly, but we are more arguing from the gradient point of view. So on this gradient, you can have this gradient for any function, right? As long as it's differentiable. Okay. So then these two conditions are actually is generic condition. Okay. It does not just apply to the example. This is a concrete example we just with the talk or the toy example we just discussed here, but it can be applied to a general scenario. So to summarize, if fx lies on constrained surface, setting this is a delta x orthogonal to this is a gradient of a constraint, ensure you move it, you still the new point is still be feasible, right? And also, then in order for the cost function to go down, if and only if your delta x times the negative gradient cost function is bigger than 0. So these are the two constraints. Okay, these are two constraints. Or we want to be satisfied. Now, when this is the third, when the gradient of the cost function is equal to some proportion of the your gradient of the constraint function, okay? The mu is a scalar here. When they are in the same direction, okay, when this occur, then delta x is orthogonal to this is a delta x is first is orthogonal to the to the constraint function. So therefore, delta x times the negative gradient, which is going to be negative delta x times mu times this is a gradient of the cost the constraint function is going to be equal to 0. So if the gradient of the when this happens, when the gradient of your cost function and the gradient of your constraint function, they are in the same direction, okay? They are same direction. You cannot move this fx to be remain on the constraint surface and decrease or the cost function, okay? This basically is you reach, if this happens, this case corresponds to your constraint local optimal. Okay, so that's this is basically this is what happened. So when this happens, then what we have is a constraint of minimum point. We've already found it. That's the way we going through this. As you can see, when we go down from here to go down here and go down here, when it's reached to this point, okay, when it's to this point, your the gradient of the cost function and the gradient of your target function, they are pointing to the same direction, right? So therefore, then this is where the local optimum point is being occurred. Now, so for this point we call it critical point. A constraint local optimal occurs at x star when the gradient of your cost function and the gradient of your constraint function are parallel. Okay, so that is then this can be satisfied. Okay, this can be satisfied. Now if this satisfied could be a local minimum or could be local maximum, right? Then to determine whether it's an optimum and the minimum or maximum, that's dependent on second order condition. Okay, so this is the first order condition we cannot tell. So from this will be the Lagrange multiplier going to make sense. So this is where we have in this is you guys should be familiar with the Lagrange multiplier. So this is where it comes from. Okay, remember our constraint problem is optimization problem is minimize fx subject to hx equal to 0, right? So if we can define the Lagrangian, L x mu will be equal to fx plus mu times hx. Okay, so then x star is the local minimum when there's a unique mu star such that the gradient of the Lagrangian function equal to 0. Okay, when this equal to 0, this is basically we're saying this is a gradient of gradient of the cost function is linear with the gradient of the constraint function, right? So this is satisfy this first thing. Now, if we this is taking the partial derivative with respect to x. If we take a partial derivative with respect to mu, then that's just saying hx star equal to 0, right? So which means the point is still feasible. And of course, the third one will be this is the second order condition to be satisfied. Now remember, when the second order when the point is feasible, okay, hx is always equal to 0. When hx equal to 0, that means your Lagrangian function equal to your cost function. Okay, so that means this is second order condition for your cost function also satisfied. So then this is so our argument basically using the gradient, the argument basically is end up with this is a Lagrangian, okay, which is you should be very familiar with. So if you have in this is a constraint, the equality constraint, you have this Lagrangian with Lagrangian multiplier mu, giving this fx plus mu hx. That's this is how it derived. Now, in the case you have multiple equality function, then you basically adding multiple mu, right? You have multiple mu here. So then but then the Lagrangian function is still the same. So that's so this is how the how things is derived. Now is this clear or any question? Okay, so this is again I think this should be pretty straightforward. Some of you may maybe familiar with Lagrangian, but probably you don't know how the Lagrangian is actually is derived. Okay, because like when I learned this is in my undergraduate study, I was taught the results, but I really don't know how the Lagrangian where it come from. Okay, so this is you can basically argue that from this gradient point of view, this could give you the Lagrangian is basically is a construction to satisfy the gradient condition. Yeah. Now let's consider when with the equality cases. When the equality cases, then if you have inequality constraint, then this can be also broken down into two cases. So let's consider first, for example. Now we try to minimize fx. Fx equal to x1 squared plus x2 squared, subject to gx less than or equal to 0. Okay, the gx will be x1 squared plus x2 squared minus 1. Okay, so now if this is our problem, if we plot it out, then again fx just be circles, right? Be circles. If without any constraint, the minimum is going to occur at the origin point, right? Because this is the 0 is the minimum point. If without constraint, we know the minimum is going to be at the origin. It's going to be 0. It cannot be less. It cannot be negative, right? So that's the smallest value. Now, if you add in the constraint, okay, add a constraint, gx less than or equal to 0. That's basically is a circle within the radius 1. Okay, with radius 1. Now, in this feasible region, this is our feasible region. In this case, okay, in this case, we know our global minimum. We know our global minimum is happened at the origin, and that global minimum is located in the feasible region. Okay, so therefore, since it's a global minimum, it has to be a local minimum, right? Because this is a global minimum is always less than or equal to local minimum. So therefore, the global minimum has to be the minimum with this constraint. In this case, okay, in this case, we can see this should be easy, right? This is easy because this is a minimization problem. Essentially, is the same as our unconstrained condition. The unconstrained condition basically is the first gradient equal to 0, and the second gradient is positive definite. Okay, so in this case, we can see our problem has an inactive constraint. Okay, the constraint is there. It doesn't play any role in optimization, right? Because we didn't use it. Okay, it's called that's the inactive constraint. So the constraint is not active at local minimum. Therefore, the local minimum is identified by the same condition in unconstrained cases, right? So that's what is unconstrained cases is basically the first order condition equal to 0, and the second order condition say is a positive definite, right? So this is the condition for it to happen. So if our constraint is inactive, it's easy. Now, what if in the case number 2, I'll be saying, what if our constraint is not inactive? Okay, is actually play a role in optimization. So in this case, we modify the target function a little bit. Okay, so we're still gonna keep our constraint to be the circle is error 1. That's still the constraint the same. But for our target function, we change a little bit. It's still going to be a circle, but we're more center to 1.1 to 1.1. It's outside a little bit. Okay, we're outside a little bit. Now, if we look at this is the contour for the global minimum, we know the minimum is going to occur at the center, right? So there is 1.1, 1.1. Now, this center in this case is going to be outside of your feasible region, because your feasible region is just a circle with a radius 1 with center at the 0, 0. So then the global minimum is outside of this is a feasible region. So in this case, okay, our constraint is going to play a role. It's going to be active. Okay, this is called active constraint. Now, if it's active constraint, okay, where the where the minimum for the target for the cost function is going to occur. Because this is for our target function is basically depending on the radius. This is just a circle gradually goes bigger and bigger with larger radius, and then it's whenever this radius is the smallest circle, we can touch the phase region. That should be our smallest fx with the constraint under this constraint, right? So therefore, if you look at these cases, what the minimum function should really just be if you increase in making the circle, okay, make a circle within the center at the 1.1121, but with this is a bad drawing, but with this is a circle, and this circle is going to be just tangent. It's just be tangent to the feasible region. Okay, so this will be your the minimum point, right? This is going to be a minimum point. Now, what does this mean? This just means your minimum point. Okay, your minimum point will always occur at the surface of the feasible region. Okay, because whenever you have in this circle for the cost function, whenever its radius increase, as soon as it touches, okay, as soon as it touches this feasible region, that is your minimum point, right? That's a minimum value. That's the smallest radius you can draw, okay? Because then you can draw another circle. It's going to be inside. It's going to be also feasible. You have feasible region, but then the radius is going to be larger than the radius you touch the surface. Okay, touch the surface. So therefore, your minimum point if your constraint is active. Okay, if your constraint is active, your minimum point going to be always occur at the surface of the of the constraint, which is surface of constraint is going to be defined at the gx equal to 0, which is defined as equality constraint. So if your constraint is active, that means your inequality problem essentially is become an equality constraint problem. Okay. So if it's inactive, then you are just doing unconstrained optimization. If your constraint is active, you are doing a minimization problem with equality constraint. Okay, so this is how it works. And we already know how to solve the problem within the equality constraint, right? We already know how to solve it. So then this is just argument. So if this is fx is a local minimum, it's not, right? Because you can see we can move into this direction. Now, so how to recognize if fx is a local point? The constraint local minimum occurs on the surface of constraint surface. Effectively, we have a minimization of any problem with the equality constraint is just gx equal to 0. Okay, so in these cases, our problem is become a problem we already solved before. So in this case, given an equality constraint, okay, the local minimum occurs at the gradient fx under the gradient the gx, which is the gradient for the cost function, and this is the constraint function, are parallel, which means the negative gradient of the fx has to be equal to the gradient of the constraint. Now, but now the sign matters. Okay, the sign matters because you have to be the negative gradient. The negative gradient of x has to be in the same direction of the gradient of the constraint function. Okay, if they're in the same direction, that's not a minimum. That's a maximum. Okay, so in this case, this lambda has to be bigger than 0. Okay, so this is negative gradient of this is a cost function which is point to the inward this point inward, and the gradient of your constraint function, which is the blue arrow, they have to be in the same direction. Okay, so therefore lambda in this case is bigger than 0. Okay, so this will be the local optimum point is occur in this case. Okay, in this case. Yeah, so this is just facing this point right here. They are also parallel. This is a the gradient of the cost function gradient of the constraint function, they are parallel, but they don't satisfy. This of course is not an optimum point, right? If the optimum point has to be the one closest to the global minimum of your target function, right? So that's so in this case, the constraint local optimal occurs when this is a negative gradient of cost function and the gradient of your cost function point in the same direction. Okay, so in this case, this function has to be satisfied with lambda is bigger than 0. Now the summary for the optimization within one inequality constraint, then this is putting two things together. Case number one is when when your constraint is inactive, right? When the constraint is inactive, the case is we have an unconstrained local minimum occurs in the fifth region, such that gx star has to be less than 0, right? Because then it's going to be not on the boundary, right? It's not going to be, it's going to be located inside. So the gx is less than 0. It's feasible, of course, it's feasible. Second is the gradient of your cost function has to be equal to 0, right? Then the third is the second order condition is a positive self-definite matrix. In this case, it's just big. If it's just one dimension, that means this is bigger than 0. So if it's inactive constraint, these three things need to be satisfied. If it's active, okay, if it's active, then this is an unconstrained local minimum lies outside of phase region. It's on the surface, right? Surface. So therefore, in this case, gx star has to be equal to 0, right? If it's in this case, then your optimum point has to be saying it's on the surface of your point. And the second, the negative gradient of the cost function is going to be in the same direction of the gradient of the cost function. They have been parallel. So lambda has to be bigger than 0. So this is and of course the second order condition has to be satisfied. Okay. So these two cases, if we can put them into one scenario, okay, put into one scenario. This is where the so-called KKT condition, okay. KKT, the name of the Tucker in here. Just a little bit history. We have a professor in the AMS. His name is Professor Alan Tucker. The same Tucker, okay, but it's not his Tucker. This is actually his father. Okay, this is his father in this famous KKT condition. So this is you guys can see we have some connection although through this weird link to the connect to the famous mathematician. So this KKT condition basically is if we can define to the Lagrangian. Okay, so if you want to minimize this is fx subject to gx less than or equal to 0, then we can basically define our Lagrangian to be fx plus lambda gx. Now this lambda has to be positive. Okay, has to be positive. Then the KKT basically saying the x star is the local minimum if there's a unique lambda star such that the gradient of the Lagrangian with respect to x equal to 0. Okay, lambda star is bigger than or equal to 0. Lambda star times gx star equal to 0 and gx star less than or equal to 0. Plus the positive definite condition, the gradient of the Lagrangian function with respect to x. This is a positive self-definite, right? So or the positive definite. Then these 5 conditions, okay, these are the famous KKT condition. Okay, these are the 5 conditions. Essentially, we can verify them. Okay, so in the case number 1, when the inactive constraint occurs, what happens? Then lambda star is going to be equal to 0. Okay, so then we have this is our Lagrangian function basically just equal to fx, right? Because the lambda is equal to 0. Why lambda has to be equal to 0? Because we know gx star is not necessarily has to be 0. Because if it's inactive, the gx star is going to be inside the phase region, right? It's not going to be on the surface. So then this not necessarily has to be 0. So therefore, lambda has to be equal to 0, right? lambda has to be equal to 0. If lambda equal to 0, then that means the Lagrangian basically is your fx, right? Is your fx. So in that case, is the KKT condition 1, that's just saying the gradient of fx equal to 0, because this is saying when the lambda equal to 0, the gradient of the Lagrangian is going to be equal to gradient of the cost function. So this condition satisfied. The condition 4 just saying the x star is a phasing point. What's condition 4? You're saying this is going to be equal to going to be less than 0, right? So this is going to be feasible. Now, if it's active, okay, when this constraint is active, then gx is equal to gx has to be equal to 0. Okay, gx has to be equal to 0. So in this case, is when the lambda is bigger than 0, the Lagrangian saying this has the gradient of Lagrangian with respect to x will be fx star times lambda gx, right? So the gradient, the KKT condition number 1, make sure the gradient, the condition is satisfied. That means the gradient of your cost function is in the negative gradient of a cost function under the gradient of the constraint. They are in the same direction. Okay, so that's then the KKT condition 3 says gx has to be equal to 0, and then the 3 says this has to be the fx, because this is the gx has to be equal to 0. Then this is going to be equal to fx as well. Okay, so that's this is basically saying the KKT condition. This 5 condition over here. It can cover the both inactive constraint and active constraint, right, in both cases. Now, if it's for the multiple inequality condition, you have multiple gx less than equal to 0. We're just adding like more terms into our Lagrangian function, and then you have this. When you both have both equality and inequality constraint into there, we just need to add in this in the Lagrangian function. We add in the mu term mu hx into there. But this mu x is we don't have any constraint on the mu x, right? As we talked before, because as long as it's moving to the direction in the negative gradient of x, that's fine. So in this case, we don't really have the constraint on the mu, but we do have a constraint on the Lagrangian multiplier for the inequality constraint. Okay, so these are the KKT condition for this both equality constraint and inequality constraint being satisfied. Okay, so that's this is all I want to say about the optimization. Hopefully, this is you're gonna find this is KKT condition. You're gonna come back again. We're gonna using this again in the discuss ADMM and also discuss SVM. So the next thing we're going to talk about is just a little bit preview. Okay, it's going to talk about this algorithm called ADMM. So if you if you have next class in the class for next week, okay, I highly recommend everybody to come, because if I want to say which class is the most important class for the whole semester, the one in the next class will be the one. Okay, so it will be pretty involved. And if you can understand the material on in the next class, you are pretty much that is you're going to be in a very good shape for the rest of the semester, because this is basically you're going to set up the foundation for all the rest. So what we're going to say is we're going to see this so-called Lagrangian dual problem. Okay, we're going to set up. You're going to still see the same Lagrangian problem, but then we're going to talk about the duality of the Lagrangian duality, and then how to use this Lagrangian duality for the optimization in the numerical algorithm, and how do we want to generate this is a problem into big data setting. Okay, so in the like I said, this is a next class will be pretty important. Okay, so to set up the foundation for the rest of the semester. Okay, so if you're coming late, you haven't signed in yet, there's a sign up sheet up front. Okay, so make sure you put your name there. For those who are on the Zoom, you don't need to sign. Okay, so that's all for today. I'll see you guys next week.